Welcome back to Symmetries and Quantum Mechanics. In the last lecture, we ended with something called Schur's lemma. I'll be proving that lemma later in today's lecture. But before I do, and the subsequent corollaries of this lemma, I want to give a bit of perspective about where we're heading with Schur's lemma and with these irreducible representations. And that is directly targeting the main question of this course, which is how do we find So this is a big question that plays a role throughout physics. If there's some set of symmetry operations that you want to be available in your quantum mechanical system, a set of symmetries that you want your system to enjoy or respect, then you face the first question, which is, how do I even find systems at all which have these symmetries? Do they exist? So we can talk about the following. Which we've sort of semi-agreed on in this course, that symmetry operations in quantum mechanics will be labeled by elements of a group G. This is great. And that we obey the laws of quantum mechanics. Quantum mechanics following postulates 1 to 4, but not the fifth postulate. And we can ask the natural question, are there quantum mechanical systems that exhibit, enjoy, or have these symmetries? And what would that mean? That would mean, according to postulate 1, that we need a Hilbert space that we would, according to postulates 2, 3, we would want to talk about states and measurements. But we don't really need to worry about that, because once you've determined the Hilbert space, states and measurements are usually a consequence or clearly defined in terms of the Hilbert space. We'd want to talk about postulate 4, which is expectation values of observables, but again, that's not something that really plays a role with symmetries. We would want, however, to have that, it's not a postulate anymore, it's a consequence. We would want that, a consequence of Wigner's theorem, we would want to every element in the group, every symmetry transformation that we want to act on our quantum mechanical system, we want that there's a corresponding unitary UG. And furthermore, if you do one then the other, it better be the same as doing one then the other. And U of the identity had better be the identity. So these U's they give us a representation of the group. That's these things that we've been looking at now for a couple of weeks. And we're effectively focusing now in on this question for the next part of the course, which is how to find and build, right? Once you've found them, maybe they're not the right ones. You want to build better ones. So find and build quantum mechanical systems which have symmetries labeled by some group. And there are really multiple strategies you might employ. And we're going to effectively look at both. And we've already looked at one strategy, and today we're going to start looking at another strategy. So the first strategy you might do is, find the atoms of representation theory. They have a name, they're irreducible representations, right? We've already defined these things. They are the smallest vector spaces, or in this case Hilbert spaces, which give you a bunch of operators which furnish a representation. And there's a list of them, and we're going to get quite close to understanding this list. So we could write these lists as sort of V1 to Vn, say. So strategy 1 for finding quantum mechanical systems which have certain symmetries is to find out all the irreducible representations. And then building them, how would you build in other quantum mechanical systems that have the symmetries? Well, there's all these operations we're allowed to do that will take two irreducible representations and give you another one. And I will just briefly, remind you that you can take the direct sum to get new representations. That builds bigger quantum mechanical systems. The direct sum is the OR quantifier. You have a particle of type V or type W. Or you could use the tensor product to build, that looks exactly like the direct sum. You could build the tensor product to build a new quantum mechanical system from an older one. That's the AND quantifier. You have a particle of type V and a particle of type W. And then you could take direct sums of tensor products to build even more complicated vector spaces or Hilbert spaces. And that brings us, of course, to the Fock space construction, where we could also talk about systems of bosonic particles enjoying a symmetry or fermionic particles enjoying a symmetry. And then the sky is more or less the limit, right? You can take more and more complicated systems built just by understanding these irreducible representations here, of which there is a finite list. And we will understand that by the end of this course. There is, however, sometimes a second strategy that works rather well. And in effect, these two strategies will come together towards the end of this course. So this is a slightly indirect way of doing it, right? You start with your group of symmetries, you understand all possible representations, irreducible ones you can build, and then you start building more complicated quantum mechanical systems to match extra features that you want. And that's kind of indirect, right? You start with the symmetries, and then you have to do a lot of mathematics and computations before you end up with a physical system. There's a whole other strategy which you can employ, and this one's, you've already seen it actually, it was very, very quick. I put it in front of you very rapidly, but I'm going to dwell on this a bit more today, and then we're going to come back to Schur's lemma and explain why these two things will eventually interrelate. So strategy B is this so-called regular representation. So in this second strategy, we start with our symmetries, G. I don't know where they come from. They could be rotations, or you have some reason for having symmetries that you care about. So you start with your group G of symmetries, and that's the input to this whole thing. You have to do physics to get to this group. I'll write down some examples. You could take rotations, right? 3 dimensions, rotations. You might want a quantum mechanical system invariant under rotations. Or you might take various other groups related to the Poincaré group and the Lorentz group, and you might take integer translations, or you might take time and rotations and so on. You may have almost certainly, when you think about something that you want from a quantum mechanical system, you'll have an idea of what symmetries you want. You probably want to translate in time. You'll probably want to translate in space. You'll probably want to rotate things, and so on and so forth. Now these are all abstract entities, right? There's no Hilbert space yet. Nowhere is there a Hilbert space. And so then you can think, well, it's probably hard, and you'd be right, to work out the irreducible representations of SO3. I mean, it's not impossible. You've done it in quantum mechanics 1. It's called the theory of angular momentum. You can work out the irreducible representations of a group like this. For this, you can do it too, and so on. So you can work these things out, but it is a lot of work that you have to do. And then sometimes you'll write down groups where you don't know the answer, where it's actually just sort of completely unknown the full list of irreducible representations. This usually happens in infinite dimensions, right? This is not in finite-sized groups. This is never a problem. And you might say, well, where am I going to find a quantum mechanical system with these symmetries? And then the answer is you think of the group itself as a quantum mechanical system. So, if you completely fail in understanding the irreducible representations of your group, or if for some reason they're so combinatorially intricate and complicated that putting them together in a way where it matches what you want is just extremely challenging, it might turn out that the group itself gives you a fairly decent representation. And what do we mean by that? So what we're going to imagine is that we have a particle that's a single quantum mechanical particle that moves on the group. So here the physical picture is that you think of the group itself as just a bunch of places where something can be. And you then imagine you have a particle that's moving around on this manifold of location. So you've got to be a bit careful about the word manifold, right? Manifold makes sense here, 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 because these three groups are what's known as Lie groups. And so they are both groups and manifolds. But this is not a manifold, it's just a bunch of points. So be careful, the word manifold is not used strictly in the correct mathematical sense here. Rather, you think of a particle that's sort of allowed to jump around on a lattice here, or allowed to move around on this, it looks like a sphere, this manifold here, it's a slightly generalized sphere, and so on and so forth. And that sort of immediately suggests what the Hilbert space should be, right? According to the general dogma of single particle quantum mechanics, the Hilbert space for a particle that's moving around on some kind of space is a set of wave functions on that space, right? It's a set of complex functions that go from the group to the complex numbers, subject to some kind of inner product, right? All right, the Hilbert space should be, how do you describe a quantum mechanical particle allowed to move on some surface? Well, you do so with wave functions, and you have an inner product on these wave functions, and you demand that these wave functions are square integrable, right? When you compute the norm on this of these wave functions, you get a number less than infinity. So you might be puzzled because, what's this thing, right? So when your group is just the real numbers, then you know what that thing is. It's just the integral, the normal integral. And when it's not, well, then you have a big open question. Turns out there is something that you can always write down. We won't write it down in this course, because for the most part of this course, I'm going to focus on finite groups where there is just a very simple notion of integration always. It's just sum over every element of the group, right? So this integration measure here needs some explaining. When you have an infinite group which has the structure of a manifold, there's some hard work to do in understanding what is this measure here, what does the word integral mean? But when you have a finite group, z over 2z, then it's effectively uniquely determined what that means. It just means sum over all the elements of the group. So there's a Hilbert space that we can put on the group. So if you imagine you have a group like the rotations, and you can visualize them as a three-dimensional sphere, then what kind of quantum mechanical system would have the group itself as its a group of symmetries? Well, the particle moving on the group. So you have some kind of wave function, right? You know, the particle is somewhere in the group, but it's not right. You have to have a wave function, and it's sort of delocalized around on the sphere. And so then the states of this quantum mechanical system, you think of them as just superpositions of all the elements of the group. And this is a position eigenket, right? Position eigenket. So that's like the particle is focused on that point in the group and nowhere else, like a Dirac delta function. So these things, I'm not going to define this mathematically, it would take longer to do that, but I think on a physical intuitive level you should be able to get a sense of what I'm saying. And then how does the symmetries act now, right? Very well, so I may have put a quantum mechanical system on the group itself, but that doesn't necessarily give us a unitary representation. Well, the answer is relatively direct. So if we now have an element of the group itself and we want it to act on this state, like we want to act on this state here. So we have some particle that's localized on the group and some wave function, and then we want to do the symmetry on it, right? So we need to have a unitary representation. We need a unitary operator which takes this state and rotates it into another state. And the answer, the physically intuitive answer, I hope now, is that it's just the thing that does the translating, the multiplying, right? You think of the group element itself as shifting everything in here. So how would that act there on, I'll use H instead of better letter. Well, it would take that state, right? So G, and then H acts on G. What would that mean? That would mean you take the point G and you translate it by H. If we have just the Euclidean space, flat space, it's kind of clear what that means, right? If I'm at the point X and I'm translating by Y, then I go to the point X plus Y. And that's exactly how this representation works. It just takes you from G, do I make it left? I guess I make it left regular. It takes you to this new quantum state here. And because G is an element of the group, then H times G is an element of the group, so that's just some new element of the group. We've done a translation. And this representation is surprisingly amazing and appears all throughout physics. Most particularly in the theory of gauge fields. So when you are looking at, in high energy physics, you're looking at non-abelian gauge theories, which are required to understand the strong interactions, for example, the weak interactions of nature, then these systems have these Lie groups as their symmetry groups, global symmetry groups, and then you want to build quantum fields from them. And the way you do it is you can exploit these regular representations like that. The other thing that's really wonderful about these regular representations is they have a copy inside them of every irreducible representation of the group. This is a statement that's only true for finite groups and compact groups, but nonetheless, it's true and therefore extremely helpful, right? Because this is a fairly explicit thing, right? We can write this down, we can understand the action of the unitaries as a very simple action. And then you learn, as a consequence of Schur's lemma and the things that we're going to do today, that inside this representation, which is a pretty big representation, there's actually a copy of every irreducible representation of the group. So in a way, you never have to work them out, right? You just start with a regular representation, start plucking out the irreducible representations. And so that's the deep connection between strategies A and B. Actually B contains all the irreps, and A can build the regular representation. So this is interplay between these two things. So that's the motivation. That's where we're headed in this course. We're not going to get much further than that. We're not going to get much further than this explanation here. But in doing so, I would have shown you the most important results in representation theory. Representation theory is a gigantic field. It's a monstrously large field. And there's thousands upon thousands of textbook pages on this topic. But the key ideas, the most important ideas, which you can take and deploy in your physics careers, can already be understood very well at the level of a couple of lemmas, in particular Schur's lemma and some corollaries. And that knowledge will help you tremendously moving forward in your physics education, because then you'll see, okay, the reason they're obsessing about this is actually they want a quantum mechanical system that has these symmetries, and that's why they're faffing around with irreps of the angular momentum. So you'll see it happen over and over again later on when you look at high energy physics, quantum field theory. Why are they talking about these Noether's theorems and momentum generators and so on and so forth? Because they want a unitary representation of the Lorentz group. It's sort of always not quite explicitly said in many quantum field theory textbooks, so you sort of miss these points. But if you always think now in the lens of symmetry, 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 then you'll understand why people are doing the things they're doing. So Schur's lemma, I don't particularly want to write it out again. I wrote it out at the end of the last lecture, so I invite you to look at your notes. And what I want to do is dive into proving it. And this is one of those lemmas where, like, the proof isn't very complicated, but you also learn a lot about how to prove things, so it's worth going through the proof. Sometimes you have a list of theorems and so on and propositions, and you get through the proof, but you don't learn anything transferable or useful for the rest of the subject. This one is definitely a counterexample to that. So what I'll do is I'll take aim at, there's two parts of Schur's lemma. Okay, well, I'm going to have to write down some stuff so that we can have the notation here. So in Schur's lemma, there are two representations, right? And there's a thing called an intertwiner. So you assume the existence of an intertwiner in Schur's lemma. Sayre never calls it an intertwiner, but that's what it's called. And an intertwiner is a map F that goes from V1 to V2. And what is an intertwiner? Well, it's something that behaves like this. If you do a group representation of a group first and then go to your second representation, then it better be the same as if I had done the intertwiner first, then the second representation. So it respects, the intertwiner respects the group action. So we suppose we have one of these things. And, well, what we're going to learn is that they're not very easy to create, and when you can create them, they're very boring. So that's a kind of a strange thing, but you'll see. That's only when we have irreducible representations. Intertwiners get fantastically more interesting when you have reducible representations. You can build these intertwiners for any two. These don't have to be irreducible. When they're not irreducible, intertwiners become much more complicated objects. But these are irreducible, so I didn't write that down. They're irreducible representations. And here, intertwiners are boring. They're the boringest things that you could get, because they're either trivial or the identity. That's what Schur's lemma says. Trivial or the identity. So in part one, we're going to say that if we have two non-isomorphic, so if V1 and V2, if there's no rotation that takes one of these representations in the other, then can there be an intertwiner? And the answer is no. No intertwiners. They don't exist. Okay. So, to make this first part even interesting, we're going to suppose that f is not 0, right? Because if f is 0, we have a solution. a solution to this intertwiner problem. Like if f is 0, then 0 times something is equal to something times 0. So yeah, then sure, there exists an intertwiner, but that's trivial, right? No one would really think that was an interesting case. So we're going to suppose that we have a non-boring intertwiner. And what we're going to do is we're going to build some subspaces of V1 and V2 that are representations of the group. And then we'll say, oh, whoops, but these things were irreducible, so the only subspaces that can be allowed are is V1 or nothing. And then we'll learn everything we need to know. So how do we build a subspace of a vector space? And if you've got some linear map acting on it, there's a couple of really standard things you should try. So the first thing is that the kernel of a linear map, right, the things that it annihilates, is always a subspace of its domain. And it might be, and we'll see, that the kernel of f gives a representation of the group as well. So this is always true. So let's take a look at the kernel of f. What does it look like? The kernel of f is the set of all those vectors in V1 such that when you do f on it, you get 0. That wasn't very hard. It's clearly a subspace of V1, right? And what else can we say about the kernel of f? It cannot be V1. Because by assumption, we said that f is not equal to 0. If f was 0, then the kernel of f would just be all of V1. So it's got to be smaller than V1. Now we're going to see that this kernel of f isn't just some weird subspace. It's got quite a lot of structure. And so suppose that you've got something in the kernel of f now. That's a vector annihilated by this intertwiner. Then let's notice something. What if we just take some element of the group and then we act on W with our representation? So what could happen is that the group could rotate that vector outside of the kernel. Could be. And we're going to ask the question, is the rotated version of W also in the kernel? Of course it is, but we have to argue that. So we've just learned that we have something in the kernel. Now we're going to act on it with the symmetry. We're going to ask, is that also in the kernel? Well, let's look at this defining property here. So what do we know? We know that f of W is definitely 0, right, by assumption. And if I act on f of W afterwards with rho s of 2, then I'm going to get 0, because I take 0 and I multiply by something, you get 0. But by assumption, f is an intertwiner, so that's the same as rho s1 acting on W. So we know that this thing here is 0, but that's equal to f acting on this. But that's the thing that we were wondering if it was in the kernel or not. And it is in the kernel because f on this thing is 0. So 0, so that's in the kernel. So we now know that the kernel is stable under the group, that the symmetries act on the kernel of f. Right? The kernel of f is a sub-representation of V1. But by assumption, we said that these representations were irreducible. The only sub-representations of an irreducible representation are the whole thing or 0. And since it's not the whole thing, it's got to be 0. There's nothing in the kernel of f except 0 itself. Now we're going to play exactly the same game with the image of f. You always get these two subspaces when you have a linear map. The kernel, the image, they're always there. So we're going to play exactly the same game. Image of f, that's a set of vectors which you get, which come from something in V1. It's a subspace of V2. So the set of vectors in V2 such that W equals f of V for some V in V1. That's what the image of F is. Also a subspace. And we're going to do exactly the same thing we just did. We're going to say, okie doke, let's apply some symmetry operations and see what that gets us. So we suppose that we have something in image of F, I don't know, call it X this time. And now we're going to act on X with a group element. Since X is in the image of F, then there exists V in V1 such that F of V is X. That's what image means. So we know that rho S acting on the vector space V2 and in particular on this element X in the image of F is the same as rho S2 of F, but that's the same by assumption of F of rho S1 acting on V. But that's a vector in V2, in V1. And therefore, this thing is in the image, per definition. Oops, the image of F. So we learn that the image of F is a subrep of V2. And by assumption, V2 is irreducible, so it's either V2 equals the image of F, that's one possibility, or V2 or image of F is 0. That's the only two possibilities that are allowed to us. But it can't be 0 because by assumption F is not at 0. So we've just learned that the kernel of F is nothing and the image of F is everything. And such a thing has a name. Right? It means that F is an isomorphism between these two vector spaces. So either F is 0 or it's an isomorphism. Right? So kernel F equals nothing, image F equals V2, F is linear by assumption. So F is an isomorphism of vector spaces. So in particular, the dimensions of V1 and V2 have got to be the same. So, but that's explicitly disallowed in case 1 of Schur's lemma. So in Schur's lemma, we said, suppose F is not 0, and suppose these vector spaces aren't isomorphic. Well, we only have one option then, F has to be 0. So F has to be 0 or an isomorphism. So now let's move to the second case then, when F is this isomorphism. What kind of isomorphism? So if V1 equals V2, which we're forced to now accept, and these representations of the group are therefore the same because we're on the same vector space now, what can we say about F? What kind of maps would be allowed And the answer is that f will actually have to be proportional to the identity. So let's see how to do that. So f is a map from v1 to, well, v2, which is the same as v1. So think of f now as a matrix, right? F is it's just a map on a vector space to itself. So it's a square matrix if we chose a basis. And so f always has one eigenvalue, at least one, greater than one. This may not be immediately obvious. So if you have a matrix acting on a complex vector space, your matrix will always have at least one eigenvalue. It may have only one, though. How can we be so sure that that's the case? Well, let's look at the definition of an eigenvalue. An eigenvalue is something where you build this polynomial, this characteristic polynomial, f lambda. This is some polynomial in lambda. And then because every polynomial splits over the complex numbers, there's always at least one root. We know there's at least one eigenvalue of this polynomial. It could be that there is just one polynomial, right? One eigenvalue it could be like this. The polynomial could just be lambda minus z, where z is that eigenvalue. That could be. Generally speaking, that's not the case, right? Usually you have things like this, lambda 1 minus lambda 2. The polynomial splits completely and has distinct roots. That usually happens, but it can happen that, of course, you have just one root that's repeated n times. Okay, so always, our linear map's going to have an eigenvalue, and we're going to call that eigenvalue lambda. Oh, that was a stupid notation. We'll call it mu. Okay, there's one single eigenvalue of f is called mu. At least one eigenvalue. And we're going to build a new map, G. What is G? Well, G is just like f. I'm just going to subtract off the identity multiplied by mu there. And now we're going to play practically the same game again. We're going to look at the kernel of G. So the kernel of G is a subspace of V1. It's a set of things annihilated by this linear map here, and it has dimension bigger than 1, or equal to 1. There's at least one vector inside the kernel of this map here. Right? Because it annihilates the eigenvector with the eigenvalue mu. So there's at least one vector inside there, in this subspace. Yeah?
If there are more than one eigenvalue, do we just pick one at random?
That's a good question. If there's more than one eigenvalue, do we just pick one at random? Absolutely. We just pick one at random. As we'll see, there can only be one. So that's the punchline. All right, so kernel. Now I'm going to argue that this kernel is also a subrepresentation of V. How are we going to play that game? Well, we act on it, on the kernel, that is. So we'll let V be in the kernel. Or will I? Not yet. First, we'll just argue that this is true. I've dropped the 1s and the 2s now because V1 is the same as V2, row 1 is the same as row 2. So this has got to equal that. Why? Well, if you insert, let's see why. Well, if I do row S and then I do F minus mu, the identity, by assumption row SF is F row S, and well, the identity commutes with everything, right? So that's the same as G rho S. So we're in exactly the same situation as in case 1. And that immediately allows us to infer that kernel of G is going to give us a representation of the group. So it's irreducible, right? V1 by assumption was irreducible. So the kernel of this linear map here is either nothing or everything. Now it can't be nothing, because there's at least one vector in it. So that possibility is, so the kernel of G is everything. G in fact annihilates every vector. And that tells us something, right? If kernel of G is everything, then that means that F must equal mu times the identity. It's the only possibility left to us. So I'm going to say what this result says in a second in completely different words, but for the moment, if we have a vector space that's a representation, and we have some other map that commutes with all the symmetries, so if we have a representation, it's the same, V1 and V2 are the same, if that, and if we have some other map that commutes with every other symmetry, so F is kind of now like a new symmetry, if you like, commutes with everything, then if the representation is irreducible, F must be trivial, it must be the identity. That's what Schur's lemma says. There are no extra symmetries on an irreducible representation. And the way I like to think of it is that F has to commute with so many things that this puts so many conditions on F that the only thing left over is just for F to be the identity. That's what Schur's lemma tells us. It may not be obvious that this is a very powerful conclusion, but it's an extraordinarily powerful conclusion. You'll see it applied in all kinds of places. So I'm sort of internally debating whether or not I give you this example. I think I probably will. So take a break from this and tell you about a physics problem. A physics problem that about 20 years ago, 10 years ago, people looked at. So at this stage, I'm going to assume you know a bit about quantum entanglement. You don't need to know super lots. You don't even need to really know the word entanglement. And I want to talk about a line of research in many-body theory, which has been, people are still looking at these kind of questions. And I believe it was around, go ahead and say like the late 90s to early 2000s, when people first started to really seriously think about symmetries and quantum entanglement. Like, if you have a quantum mechanical system with some symmetries, what can you say about the entanglement of that system? And so I'll give you a little toy version. And And this is, in this toy version, you know, you could quickly learn that there's a very interesting interplay between symmetries and entanglement, and Schur's lemma gives it to you. So I think it's kind of cute that we should have this. So we imagine we have two particles. V. So V is a Hilbert space in this particular case. So I'll just do that. Hilbert space. And these two particles, they have some symmetries, right? They're very nice symmetric particles. So they're symmetric under a group of symmetries. Now you can take the context in which I learnt it was the group SU2. But we don't have enough examples of finite groups yet for me to give you one where I could give you a result quickly. Yeah, the dihedral group. So we have these two particles, and that's the Hilbert space. And we imagine they're quite small particles. We imagine they're quantum bits, right? They're just two-level quantum mechanical systems. So this was very, very... people got interested in these quantum mechanical systems in the early 2000s because quantum information theory was starting to become relevant and popular, and quantum computers, the first ideas about quantum computers were being developed. And we imagine that we have these, then people start to ask the question, well, what if our qubits, our quantum bits are symmetric? They're a quantum mechanical system with symmetries. And so the first symmetry groups that people thought about actually weren't dihedral groups, but actually SU2, which is the angular momentum group. And it's known, right, that C2 gives an irrep, or furnishes, so C2, a qubit, furnishes an irrep of this SU2 group, the group of angular momentum. And how does it give that irrep? Well, this is super easy because SU2 is the group of unitary matrices A, B, C, D. So SU2 is a set of these things, which we'll call G, such that G dagger G is the identity, such that they're unitary, right? And G dagger. So C2, how does it give an irrep of SU2? Well, the most obvious way possible, right? You just let these unitary matrices act on the two-dimensional vector. So then you might ask the question, okay, yeah, let's suppose we have a quantum mechanical system made of two particles. They're each very symmetric, but together it's a tensor product, right? That means we've got two of them. We even know how the symmetries act on this global system. So if you have G in SU2, then the representation of G on H tensor H is just do it twice with a tensor, right? So we have our quantum mechanical system, and what I'm going to say generalizes to many particles, but let's just stick with two for the moment. And then we suppose that our quantum mechanical system has these symmetries, and these things, you can build them all the time. You have two spin 1/2 particles, right? Right? A qubit is also otherwise known as a spin 1/2 representation of the angular momentum. So you've built these things. So we have two spin 1/2 particles. Symmetry group acts on it. And then we imagine that we want to have some system, some dynamics acting on this quantum mechanical system that's invariant under SU2, invariant under rotations. So we're going to extend the group here. So we started off with SU2. And now we want to add some dynamics into the story because SU2 is only about rotations. It's only about angular momentum. SU2 as a group of symmetries doesn't tell you about time. There's no time There's no time in this story, right? All I can do is rotate around some axis. So how do I even represent time in this story? Well, we have to choose a new group. And the new group that we build we'll call M, and it's just the real numbers cross SU2. So R represents time, and SU2 represents rotations. And we want to build a representation of that group on this Hilbert space. If we manage that, then we will have solved Schrödinger's equation along the way. And indeed, the best way to do it is to use Schrödinger's equation, right? So, you know, talking about representations isn't the magic formula to quantization. Usually you just have to do normal quantum mechanics and then argue that you have a representation. Going the other way around is seldom somehow efficient or good to do. Also, here's an interesting point to talk about the regular representation and how different that is from this setting. So, just one of these particles, these spin half particles, is a two-dimensional complex vector. It's a qubit. If I built the regular representation on SU2, then I'd have an infinite dimensional vector space. So SU2 is, roughly speaking, it's this three-dimensional sphere as a manifold, and the set of all wave functions on the three-dimensional sphere is infinite dimensional. So this representation here, this irreducible representation of spin 1/2, is extremely different from the regular representation there. And that in turn is extremely different to the regular representation on R cross SU2, which is even more infinite dimensional. So one thing you should bear in mind is that irreps are kind of small, and that the regular representation is kind of gigantic. So we want a regular representation of this group so we can add time into the story. So then we can do time and rotations. Now, the most efficient way is as follows. You just find a Hamiltonian that plays nicely with the other part of the group. So that's the easiest way. And then you solve the Schrödinger equation. So we're going to do it that way. I would love for there to be a more kind of elegant way to do it, but that's the way I would know. So we want to find a Hamiltonian that commutes with the other part of the group, such that G, tensor G, commutator with H is 0. And then I claim if you can find such a Hamiltonian that commutes with the rest of the group for all G, then this gives a unit. This will give us what we want. So then we're going to build now. If suppose this thing exists, like you can at this moment you can say I don't believe that H exists. You're welcome to say that right now. but it does exist because there's at least one operator which has that property, right? And that's the identity. So there's at least one Hamiltonian which commutes with all the elements of the group, and the Hamiltonian is the identity. There are others, actually. This Hamiltonian isn't the only one, and I'll write down an explicit one presently. So then we're going to finally get our unitary representation of time and rotations. And how do we build it? Well, suppose you have time t and rotation g, then the unitary representation of translating by time t and rotating by g is given by g tensor g multiplied by e to the I t h. So you have to argue, you have to think, is this thing a unitary representation? What does it have to obey? It has to be a homomorphism, right? So what happens if I try and find the unitary representation of translating a bit more and doing a second rotation? Well, according to the definition right there, that's gh tensor gh multiplied by e to the I s plus t h. But this h commutes with g, t h s h. There you go. So this unitary matrix here is a unitary representation of M. So as long as you can find a Hamiltonian that commutes with all your rotations here, then you're golden and you have a unitary representation. So do they exist? That's the next thing we have to argue. Yes, they exist. Here is one. That's a Hamiltonian that commutes with all rotations. That's something you have to prove. It's an exercise. It's not that hard of an exercise. This one, does it? Yeah, has a unique ground state even. So now we get to the application of Schur's lemma. So this Hamiltonian has a unique ground state. This is now we get to the actual result that was proved and has been the topic of discussion. So we imagine that we have a quantum mechanical system. It's symmetric under these group of rotations, and we suppose, we have a unique ground state, right? There's no degeneracy. It's got this one ground state. There's all these excited states, but there's this one ground state, and there's a spectral gap. And then we ask, how much entanglement is in this ground state? So we'll give the ground state a name. Omega. So your system is pretty simple. It's got a unique ground state, and you can ask, if I just look at part of the ground state, will that be very mixed or not? So what you have to know and what you can easily look up is if a quantum state is entangled, then the reduced density operator of 1/2 of the system is very mixed, right? So that's the thing that you'll have to take for granted. And if you don't know that, then just accept it. So what we're going to do is we're going to write out the reduced density matrix of the ground state for spin 1. What does spin 1 look like? If you just threw away spin 2 in the ground state, you have the ground state, there's these two spins, these two particles, and you put one away. Just ignore it, don't look at it. What does the reduced density operator look like? What does just one spin look like? What does one observer who can only observe that one spin, what would they say? Well, they'd say, well, I'm going to have to work out the reduced density matrix. And I'm going to do it like this. I take the partial trace over the second tensor factor of the ground state, like so. So far, whatever, right? Or when you do this calculation, you'll get some kind of 2 by 2 matrix. P 1 minus P x star. So why is it P 1 minus P x star? Well, P has to be greater than or equal to 0. 1 minus P has to be greater than or equal to 0 for this to be a density matrix. The trace has to be 1. It has to be a positive operator, so that means it's at least Hermitian. So x is going to be equal to x star there, upon Hermitian conjugation. So we know that whatever comes out of this reduced density operator is going to look like that. But we know one more thing. We know that the group commutes with the Hamiltonian. Okay, so I guess I have to tell you about another thing. So if some unitary operator commutes with a Hamiltonian and the ground state is unique, then G tensor G on omega equals omega. Actually, I've already proved it, right? When I went through Schur's lemma, I did exactly this. I said you've got an eigenvector and an eigenvalue, and you learn that the kernel is also a representation of the group. And there, I've just applied exactly that result in the proof of Schur's lemma to learn that the ground state is also a one-dimensional representation is a sub-representation of SU2 here. And now we're going to learn the final thing, right? And that is this. So we know some facts now. I'm going to put colors around these facts. So this is a definition. There's this unfortunate collision of notation here. Rho is density matrix here, but rho meant representation earlier in the lecture. I hope you'll forgive me. Rho has nothing to do with the representation here. It's a density matrix. Actually, probably I could just make life simpler for everyone if I call it sigma. Right? Then there's less danger of anyone sort of looking back and going, why is the representation there? Sigma. Okay, that's a fact. And here's another fact, right? Now, we're going to put these two little facts together and Schur's lemma, and we're going to learn something quite amazing about the reduced density matrix. So let's take the reduced density matrix and multiply it on the left and right by G. Well, by definition, that's the trace out of G tensor the identity on omega, G dagger tensor the identity, like that. But by the cyclic rule of partial trace, I can put in a G and a G dagger here. Because I'm taking the trace on the second tensor factor, I can always put things in the second tensor factor. So this is equal to G tensor G omega, omega, G dagger tensor G dagger. right? I could cyclically just move the second factor around and annihilate it away. But let's look at this second fact that we know here. That's just equal to sigma. So we know for all rotations, g sigma g dagger is equal to sigma. There's another word for this. That's the same as saying that g sigma equals sigma g, or that, well, that's already enough to apply Schur's lemma, of the commutator is 0. But now we can apply Schur's lemma, right? We're in that situation, exactly the situation of Schur's lemma. We have a linear map, namely sigma. Sigma acts on our irreducible representation to itself. Sigma goes from H to itself. So it commutes with every single unitary representation of the group. So there's only one conclusion left over to us, and that is that sigma is proportional to the identity. So P is a half, and X is 0. Because it has a trace 1, right? A density matrix has trace 1. So 23 years ago, you would have got a scientific paper out of this result. Nowadays, it's kind of taught at undergraduate level. So what's the conclusion of this argument? The conclusion is if you have a symmetric system built out of some particles, and you have a unique ground state for that system, then how much entanglement is in the ground state? The answer is a lot, like really a lot of entanglement is in there. Because the reduced density matrix for spin 1 is completely mixed. That means that its effective temperature is infinity. So temperature of the reduced density matrix is proportional to entanglement. And this result holds not just for 2 particles, but for n particles. So you can play this game. I hope you can, as an exercise, you should just do this for n particles. Right? And, with SU2 acting like this, just as a tensor product. So symmetry and entanglement, they have a strong interplay. And in particular, if you want to be symmetric, then you have to be strongly entangled, and vice versa. So symmetry breaking a symmetry leads to lower entanglement in quantum mechanical systems. So this is a tiny example, but I made a much stronger statement just then, which was if you have a quantum mechanical system that has symmetries, then you have 2 options. Either the ground state is highly symmetric, or you break the symmetry, so the ground state becomes degenerate, and then you can have lower entanglement. This is a general statement. People have the sort of general understanding of this. And how do you prove it? With nothing more than Schur's lemma. So I'll write that down because it's a kind of nice consequence here. So you need symmetry breaking to get low entanglement in a quantum mechanical system. Symmetry breaking means the ground state is no longer unique. It's no longer a non-degenerate space. And that's this kind of very, very general argument that applies to, I did it for SU2 and 2 spin 1 halves, but anytime you have any group of symmetries and you have an irreducible representation, you can learn this. And this is one of the reasons why we think symmetry breaking even takes place, right? Because of decoherence, we don't expect systems to be very entangled in nature. So we expect them to find themselves in low entanglement states. But the only way that can be compatible with symmetries is if the ground state itself isn't unique for the time generator. And there's almost a thermodynamic quality to this result as well. The reduced density matrix looks very hot in a symmetric system. If you want it to look cold, then you also need that the symmetries are broken. All right, that was a little physics interlude. And I certainly invite you to think about tricky applications of Schur's lemma, because they always happen when you think about symmetric quantum systems. You always start thinking, I wonder if Schur's lemma could help here. Then all you have to think about is, how do I get an irreducible representation out of it somehow of your system? And then see that something commutes with these symmetries, and then boom, you learn something deeper, like that the entanglement is high. All right, let's start working. Let's go back to Schur's lemma and see how far we can push Schur's lemma. Like, what can we get out of this one lemma? And the answer is a surprising amount, like really a lot. And we're going to use the two tricks that we have at our disposal, right? We have two tricks that you've learned so far in representation theory. You've learned Schur's lemma, and you've learned the averaging trick. So let's see how far we can push this. So we assume, just as before, that we have two irreducible representations of our group. And we suppose now we have some linear mapping. Not even going to assume it's an intertwiner anymore. So it doesn't commute with the group action. So H is just whatever, it's just some linear map. What can you do? Well, there's not a lot you can do, right? Because we can't use Schur's lemma because it doesn't intertwine with the group. But what we can do is we can take this linear map and we can build a new one which does intertwine with the group. This is the averaging trick, right? So what we do is we take H and we build a new map. How do we do it? Well, we just sum over all elements of the group. And build the following map. So little g in this case is just the order of the group. Okay, there's some danger of interference of notation with the previous example. G is the order of the group. From now on. So what do we know about H naught? Well, H is somehow like H. All we're doing is H, but we're sort of doing a symmetry and then undoing the symmetry afterwards. Okay, the first half should be kind of no surprise, and neither should the second half. I mean, all I'm doing is now applying Schur's lemma to H naught, right? So the hard part of this corollary is to really argue that H naught commutes with the group, and that's not very hard. So if these two representations are isomorphic, however, then what do we know about H naught? Well, there's only one thing H naught can be. H naught is 1 over n trace of H times by the identity. It's proportional to the identity. And n is the dimension. Oh, my. And it's just, you know, if H naught commuted with the group, it's just doing the corollary, right? It's just doing Schur's lemma on that map. So H naught plays the role as F. So all we have to do to prove this is to convince ourselves that H naught obeys this extra condition of Schur's lemma. So, question. Is this true? Because if that was true, then H naught fulfills the conditions of Schur's lemma and we're done. And I think I can do that pretty quick. Okay, first step is to multiply from the right with rho S1. But this is a representation, so that's the same as rho TS. And now we're going to change variable on the summation. So you've seen me do this before in the seen me do this before in the averaging trick when I did it earlier in the lecture course. And then at this point, if you just multiply out or expand out this inverse here, then we're done. Okie dokie. So now I have to explain where this trace factor comes from, right? Well, I'm not. That's an exercise for you. Just take the trace of both sides. Good. Let's talk about matrices. So this result is pretty amazing. Turns out this result is like a little machine. It's a machine for pulling out representations out of bigger representations. I won't be able to get to that today, or nor in the next lecture, but in following lectures we will see how applying the yellow box procedure allows us to cut out pieces of bigger representations, and in particular the ones we want. So we know that decomposable representations have lots of irreps inside them, but you can't really pull out the one you want in a targeted way. But when you take this thing here, in a couple of lectures, and you add in these characters, you'll see that you can pull out specific irreducible representations from a bigger one that you want, the ones you want. So that's coming up. But before we do that, let's just get practice with this expression as a matrix. What is this saying as a matrix, right? So H is a rectangular matrix in general, right? You know, V is some vector space, V2 is some maybe bigger or some smaller space. So H you could think of as a kind of rectangular matrix like that. You know, it takes smaller vectors and maybe gives you bigger vectors. So think of H as a rectangular matrix. And H naught is also a rectangular matrix. So let's just draw this as in kind of matrixy way. So the equation in the yellow box says that equals 1 over G, the sum over elements of the group. And then we've got rho T2 inverse. Well, that's some matrix. It's a big matrix in this particular illustration acting on V2. So it's just some matrix, big matrix. I'm going to call it R, and it depends on T inverse. So some big matrix, big square matrix. You know, acts on V2 and takes you to V2. And then in the middle, you have H, which is a matrix. And then on the right, you have a kind of smaller matrix, right? So these double lines indicate this is the table of all the entries of the matrix. So this equation in the yellow box is a matrix equation. It's an equation where you take a little matrix called R1, multiply it on the left by this rectangular matrix called H, and multiply it on the left by a bigger matrix, R2 of T inverse, sum over all T. You'll get some rectangular matrix, and we'll call it H naught. And we know some quite interesting things about the result, right? Not just anything comes out here. In fact, as soon as the dimensions are different, that's 0, right? So as soon as the dimensions of these two representations is unequal, then the left-hand side is always 0, always. That's the result of the corollary there, row 1. Part 1 of the corollary says that it's always 0. Lots of zeros. So no matter what you put in here, you know, there's lots of freedom, right? You know, H, you can put whatever matrix you like in here for little h. But no matter what you do, it's going to be 0. This thing annihilates everything inside there. And what about if dimension V1 equals V2? Well, then we have a square matrix. Okay. And then we learn that the only thing that you could possibly ever get here is the identity matrix or nothing. So either you get 1, 1, 1, 1, 1, 1, 1 equals the right-hand side, or you get 0, 0 equals the right-hand side. and, well, proportional to the right-hand side, sorry. And which of these two circumstances you get depends on the trace of this matrix here. So if you put in a traceless matrix in here, so if H has 0 trace, then it gets annihilated and you get 0 on the left-hand side. If the trace is 1, then on the left-hand side you just get the full identity matrix. So these hints that the matrix elements themselves here of these matrices, they have some weird properties. They have some weird orthogonality properties. So it points to the matrix elements which we'll call R, J, K. They're very special. Now remember how at the beginning of this lecture I talked about the regular representation. This is the space of all wave functions on the group. Well, what do we learn about the space of all wave functions on the group? From this result we learn that we have a basis for that space given by these matrix elements because, and this is the key insight and one that we'll come back to in the next lecture, RJK, you can think of that as a function on the group. Right? RJK depends on T, the element of the group. It's really a function on the group that goes to the complex numbers. So the matrix elements of your representations here you can think of as quantum mechanical wave functions on the group. Each matrix element, RJK. Right? It's a little machine. You give it a group element and it gives you a complex number. Otherwise known as a complex wave function on the group. And further, we're going to learn from this one result that the set of all these matrix elements gives you a basis for the regular representation. So that means any wave function in your group is a linear combination of these RJKs, and well, there's another number up here which is which irreducible representation you're in. Like there's these elements for each irreducible representation, right? So, okay, that's coming up, and that's already you should sort of start to sense the truth of this from the boxed equation. The boxed equation actually tells you directly that what I just said is true. But we have to work a bit, right? So I'm not going to come for free. But that's it for today. Thank you very much.